So hello everyone, welcome back to another video on Pepcoding's channel. This video is all about introduction to graphs, right? So we'll be starting with a new data structure, which is graphs, which is a fairly advanced data structure to work with. But after this video, you will be completely fine with working with graph, right? This video contains the details about what graph is and how we can construct a graph, right? So very first thing that I would want to do is create a graph, right? So the topic is graph, and if I had to create a graph, what do I have in graph? So graph has two components, right? First is vertices and second is edges, right? So a graph has two components, which are vertices and edges. Vertices are connected by edges, right? Let's draw this to understand it a bit more clearly, right? So if I had to draw vertices are just nodes. You can represent vertices as nodes, right? So I have vertices like 0, okay? Then I have 1, then I have 2, then 3, then 4, 5, and 6, right? These are my vertices. 0, 1, 2 over here, 3, 4, 5, and 6. Right now, these vertices would be connected by edges, right? So if I had to draw edges, these would be my edges, okay? So 0 and 1 are connected with an edge, right? 1 and 2 are connected with an edge. 2 and 3 similarly. 0, 3, 3, 4, 4, 5, 5, 6, and maybe 6, 4 again, right? So my vertices in this particular graph, if I had to write, are 0, 1, 2, 3, 4, 5, and 6, right? And usually in question, what we have are vertices which start from 0 till n, right? For sake of simplicity, so that we can create a graph more easily, we take vertices from 0 to n, right? So usually our vertices tend from 0 to n inclusive, right? And what do we have are edges, right? So there is an edge between 0 to 1, there's an edge between 1 to 2, there is an edge between 2 to 3, then 3 to 4 also has an edge, 3 to 0 is another edge, and then we have 4 to 5, then we have 4 to 6 as well, then we have 5 to 6, right? And 5 to 4, right? And 6 to 4, right? We also have 1 to 0, right? Now if you see closely, what I have written over here are 1 to 0 to 1 and 1 to 0 are two separate edges, 3 to 0, and of course 0 to 3, these would be separate edges, and 4 to 6, 6 to 4 are separate edges, 4 to 5 and 5 to 4 are also separate edges, right? I missed out some cases in between, which were 2 to 3 would have 3 to 2 over here somewhere, right? 3 to 4 would have 4 to 3 somewhere, right? So the basic idea is every node can travel to and back to its destination, right? What do I mean by that? If I have an edge between 0 to 1, I can travel from 0 to 1, and I can also travel from 1 to 0. So we can say that there is an edge between 0 to 1 through which I can travel from 0 to 1. That means my source is 0 at the moment and my destination is 1. And there is also an edge from 1 to 0 in which my source is 1 and my destination is 0, right? So the single edge represents that there is a connection between 0 to 1 and 1 to 0, right? So I hope this is clear. And till now, what we have discussed is what are vertices and what are edges, and how the graph is the combination of both of them, right? Now, another concept is that these edges can at time contain some weight, right? So these edges can also have some weight. You can think of the weight as cost to travel from one node to another node, right? A cost of the particular edge if you want to travel from that edge, right? So let's take an example again. If I have 0 to 1 over here, let's say this edge in between 0 to 1 has a weight of 10, right? 1 to 2 has a weight of 10, 2 to 3 has a weight of 10 again, let's suppose, and 0 to 3 has a weight of 40, right? 3 through 4, let's take 3, 5, 6, 9, right? Random numbers, right? So what are these weights? What do they symbolize? They symbolize that if you want to use the edge 0 to 1, right? If you want to use the edge 0 to 1, you would have to give a cost of 10, or it would take a cost of 10, right? You can visualize this graph as a map of a city, right? In which these vertices are major points in the cities, and these weights are nothing but the distance of the road. So to travel from location 0 to 1, it would take you maybe, let's suppose these weight represent the timings, right? So it would take you 10 minutes, right? And to travel from location 0 to 3, let's suppose you would take 40 minutes, right? I hope you understand the fundamentals of what are weights, right? So till now what we have discussed is vertices, edges, and how those edges can at time contain weight, right? And also how vertices are usually indexed from 0 to n, right? In real life applications, just now as we talked about a map, right? A map of a city, we would have nodes as locations, right? We would have nodes as locations. What we would do is map those locations to numbers, right? In that way, it would be easier for us to make a program out of it, right? We can easily assign numbers to the nodes, right? So this is how we use graphs in real life, right? Now graphs has multiple type of questions, right? So we would have questions in which we would be provided a random source. So let's suppose my 0 is the source, right? And then the question would also provide us with a destination. So let's suppose 6 over here is my destination, right? So the question would be maybe haspath, right? Haspath is a question in which you have to determine whether there is a path that exists from given source to destination, right? So if 0 is my source, 6 is my destination, then there surely does exist a path, right? So I can travel from 0 to 6 by using this path, or maybe even this path, right? Or maybe even this path, right? So there are multiple paths, right? And there could be another question which is print all paths. As we saw, there are multiple paths, so we can have question like print all paths, in which we would again be given a source, a destination, and what we would have to do is print all the paths that exist such that I reach my destination if I start from my source, right? So if I had to print paths of this particular graph for source 0, destination 6, it would be something like 0, 1, 2, 3, 4, 5, 6. What does this mean? This means I go from 0 to 1, then I go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, right? And another path would be maybe 0, 1, 2, 3, right? And then 4, and then I directly go from 4 to 6, right? So this is another path, right? Another path could be I directly go to 3 from 0, right? Rather than taking a route via 1 and 2, right? So it could be 0, 3, and then 4, 5, 6, or maybe 0, 3, 4, and then directly go to 6 from 4, right? So these are 4 possible paths from 0 to 6, right? So again, this could also be imagined as an real life application of maps of a city, right? If you have a source and a destination, maps would show you different routes that you can take to reach a destination, right? So by maps, I mean Google Maps, right? If you use Google Maps, if you enter certain destination and you are standing at a certain source, what it would do is it would look for all the possible routes that you have, and out of those routes it would suggest you the best possible route, and it would suggest you that by using by keeping cost as the timing, right? So the least time that it would take you to reach the destination is the route that it would show you, right? Okay, so these are the applications of graphs, some of the application of graphs. Another application could be to, again, to just how we discussed, the least cost path, right? So out of all of the paths that you have, what is the path that has minimum cost, right? Okay, so now that we have discussed what graphs are, how graphs are made, let's discuss how we can program graphs, right? Okay, so how we can program graphs. There are two basic ways, two most used ways to program graphs, right? To represent graphs in programs. The very first one is adjacency matrix. So adjacency matrix, right? Which basically means representing a graph using matrix. So what we would do in this case is create a 2D array, which would be of the size n cross n, where n is the number of vertices that I have, right? So in this case, my n is 7, right? So it's 0, 1, 2, 3, 4, 5, 6. That means I would create a matrix of 7 cross 7, which would have indexes from 0 to 6 rows and 0 to 6 columns. So if I create that, okay. Okay, so I would have 7 columns, 1, 2, 3, 4, 5, 6. This would give me 7, right? And then 1, 2, 3, 4, 5, 6, and this would give me 7, right? So this is extra. Remove this. Okay, so what is an adjacency matrix? In adjacency matrix, we create a n cross n matrix, integer matrix, and they have the indexes varying from 0 to n minus 1, which are my vertices itself. So I would have 0, 1, 2, 3, 4, 5, and 6 over here, and 0, 1, 2, 3, 4, 5, and 6 over here, right? So if you look at this graph, if you look at this graph which we have over here, right? If I take this graph, if I take this graph below, right? And if we come over here, we can see that there is a edge from 0 to 1, right? So what I would do is in 0 row and 1 column, I would write the weight, right? So weight over here is 10. That means I have to pay 10. I have the cost of 10 from traveling from 0 to 1. Also, similarly, I also have a cost of 10 from traveling from 1 to 0. So for 1 to 0, also I have 10, right? As we discussed, we can travel back and forth through these edges, right? Like this. That means we would fill in 1 to 0 and 0 to 1, right? The weight. Okay. Another point that we have over here is 0 to 3, right? So 0 to 3 would have weight of 40, and 3 to 0 would also have weight of 40, right? 1 to 2. So 1, 2 would have a weight of 10, and 2, 1 would also have a weight of 10, right? Then 3 to 4, that means 3, 4 over here would have a weight of 3, and 4, 3 would also have a weight of 3, right? Then 4, 5, right? 4, 5 would have a weight of 5. Then 5 and 4 would also have a weight of 5. 5 to 6 now. 5 to 6 would have a weight of 6, and 6 to 5 similarly would have a weight of 6. 4 to 6 also would have a weight of 9, and 6 to 4 would also have a weight of 9, right? So what we have done right now is fill our graph with all the information we had, right? So this row could be my source. These columns can be my destinations, right? So if this is my matrix M, then matrix Ij would represent that there is a cost, there is an edge that exists from I source till J destination, right? And in this case, as it is a graph which has the capability in which we can travel back and forth, that means my Mij would be equivalent to my Mji, right? I can switch the source and destinations with each other, right? I can swap those. Now, what would we fill in the rest of the matrix? If you notice, the entire diagonal over here, I had to show you like this, the entire diagonal over here is empty. This is because if you see over here, my source and destination are the same. So what I'm saying is, from 0 to 0, what is the cost, right? If I am at the location 0, what is the cost for me to reach 0? That would be 0, right? So my entire diagonal, which has I and j equal to 0, what I would do is I would simply add 0 over here, right? Because there would be no cost from me to travel till me, right? To travel to the same location in which you currently are at, you won't do anything. You would just stay there, right? So the diagonal is 0. Then what about rest of the part? There is no edge between, let's suppose, 2 to 0, right? 2 to 0 does not have any edge, right? So what would we fill over here? we can fill a invalid value, right? In this case, let's suppose the invalid value is -1. So what we can do is we can fill the rest of the matrix with -1, right? So this entire part would be filled with -1, right? I hope you understood what we did over here, right? Now this is adjacency matrix. This is adjacency matrix. The good thing about adjacency matrix is that you can determine whether a edge exists between source to destination in O1 time, right? Constant time. That's because you can directly access the edge by using I and j, right? But the bad part is that when we don't have an edge, when our graph is very much scattered, right? Like in this case over here, if I draw green lines over here, then this entire space is empty and unused. This is unused, right? This is unused. It's just representing that there is no edge in between those places, right? So this entire portion is of waste, right? So if we imagine this was a very small graph of 7 cross 7, let's suppose we have a graph which is 10,000 cross 10,000. That means a graph that has 10,000 edges. In that case, it would be a huge loss of space, right? Using adjacency matrix does give you access to edges in O1 time, but it is not space efficient, right? That is why we have another way of programming our graphs, which is using adjacency list. How would I create an adjacency matrix using this graph, right? So my adjacency matrix is just an array, which contains information about each and every edge, right? So my array would contain what? Would contain all the vertices, right? And let's suppose these vertices are my source. So what I would do is I would have source over here, which are simply my my indexes from 0 to 6, right? So this would be an array from 0 to 6. So I would have something like an array over here, right? And this array goes from 0 to 6. So I would have 0. I take pen, 0, 1, 2, 3, 4, 5, and 6. Right? So these are my vertices. And let's suppose these are my source. Right? These are my source. Now, what I would store in correspondence to these source are the values of my edges, right? So the edges from 0 are till 1 and 3, right? So there is an edge from 0 to 1, which has a cost of 10. This is my first edge. Let's suppose E1, right? Then there is also an edge from 0 till 3, which has a cost of 40. These are my only two edges that go out from 0, right? I'm not considering edges that come to 0 because currently 0 is my source, right? Similarly, if I write from 1, I have two edges from 1. First goes to 0, right? First goes to 0 from 1. So over here, I would have 1. Then it goes to 0 with a weight of 10, right? So in edges, if you see the structure of an edge, is what? The structure of an edge is that my edge contains a source, it also contains a destination, and then it also contains the cost, right? So my edge represents the source, where it's from, the destination where it's going to, and the cost that it would take, right? And if I had to write another edge from 1, it would be from 1 to 2 with a cost of 10, right? These are the only two edges from 1 over here, right? Then if I had to write from 2, there is an edge from 2 to 1 of cost 10. Then there is also an edge from 2 to 3 of cost 10, right? Then similarly from 3, if I had to write, I would write 3 to 0 of 40 and 3 to 4 of 3. Similarly from 4, I would have 3 to 3, 3 to 4 to 3 of cost 3, and 4 to 5 of cost 5, right? From 5 also, from 4 we have 3 edges, right? So 4 to 3, 4 to 5, and 4 to 6, right? So we would have 4 to 6 from cost 9, right? Then from 5, we can see we have two edges, 5 to 4 and 5 to 6. So 5 to 4 of 5 and 5 to 6 of 6 cost, right? And then from 6, I have 2 that goes from 6 to 5 and 6 to 4. So 6 to 5 of cost 6 and 6 to 4 of cost 9, right? So this is how I can code my adjacency matrix. This is adjacency matrix of this particular graph, right? The adjacency list, sorry, it's adjacency list, right? So this is my adjacency list. If I had to write over it, this is my adjacency list, right? Now, what is the benefit of this adjacency list? If you see over here in this adjacency list, you don't have any extra space, right? The space that you're utilizing represents the edge, and you're not storing values for edges that don't even exist. So for graphs which have huge number of vertices, let's suppose 10,000, you would only be storing all the edges that there are, right? You won't be storing information about all the points that don't have an edge. You won't be storing any information from 0 to 2. Over here you don't have any information from 0 to 2. You only have information from 0 to 1 and 0 to 3, right? That means this is space efficient. Although the downside of this is, in adjacency matrix you had access to an edge in open time. But in this case, if you had to, let's suppose, again, if you had to recognize whether there is an edge that exists from 0 to 2, what you would have to do is you have to go to 0th index in the array that you have, and in 0th index you have to look at all the edges that you have from 0, and then you have to check basically that do you have an edge which has destination equivalent to 2. If yes, then you surely do have an edge from 0 to 2. If not, then you don't have an edge, right? So in this case, there is a linear time complexity in determining whether a edge exists, right? So this is adjacency list and this is adjacency matrix. However, we would be pursuing adjacency list, right? So we would be writing our code from now onwards. We would be programming our graph, writing our code for graph using adjacency list most of the times, right? Most of the times there would be certain questions in which you would see a matrix being represented as a graph, right? So if we look at the code over here that we have, right? If you look at the code over here that we have, what we have is a edge class, right? And in the edge class, as we saw, a edge has basically three things, which are source, neighbor, and weight. What we have over here are source, which is my integer, then neighbor, and then weight, right? Using this, what we would do is, using this edge, we would create our graph. So how can we write our graph? If we see, our graph is an array, right? Our graph is an array of edges, right? Array of edges. So what I'm going to do is I'm going to create an array of array list which would contain edges, as if we see over here, the number of edges are not constant. Over here, if we see in case of 4, we have 3 edges, right? But in other cases we have 2 edges, right? That means we have to take a dynamic array, and for that reason we would have an array list, right? So what I would do is I would have an array list, and this array list would contain what data type? It would contain edges, right? So I would have array list of an edge, right? So each position inside the array list would contain information about the edge, right? And this would be an array. So an array of array lists which contain information of edge, right? And this would be my graph. I would initialize it like this, right? Over here. So this is my array initialization. The very next thing that I have to do is recognize that in this graph, as we have an array of array lists which basically contain edges, I would have to determine what would be the size of this array. That means what are the number of edges in the graph, right? So what you have to do is write over here the number of edges in the graph, which would be my capital N. So let's suppose I have 7, right? So there are a total of 7 vertices in my graph. So what I can write over here is N. All right. Now, next thing what I have to do is initialize each and every array. So what I can do is traverse to this array and initialize each and every position in the array, which is my array list. So int I is equal to 0, I goes to 7, which is my N, right? And graph of I, that means each and every position inside my array should have a array list, right? So initialize that with the new keyword, that means give it any space in heap, right? So now what I have to do is I have to write the edges. How can I write the edges? So let's suppose I write edge for source 0. What I can do is graph at 0. This would be my source, right? From source 0, what are my edges? I have to add what? My edge. So new edge. And what does this edge contain? Source, neighbor, and weight, right? So neighbor is just the destination, right? So source, neighbor, and weight. So from 0, I have an edge till 1, which is of cost 10, right? This is what it means. So it means this particular line means that from 0, I have an edge till 1 that is of cost 10, right? And I then store this edge information inside an array list, and that array list is present at graph 0th position, right? So the array of graph at 0th position, I would have an array list in which I would store the data of this particular edge, right? Okay, if I had to write another point, I can write graph from 0 also has an edge till, if you remember, I had an edge till 3, right? So 0 to 3, which is of cost 40, right? So if we go back over here, you can see that what we have is an edge from 0 to 1 of 10 and 0 to 3 of 40, right? And this is how my edge would look. If you see over here, this is my edge. This is my edge, right? And this entire portion in which my edges are stored is an array list. And this array list is stored at the 0th index in the graph array, right? So from 0, there are 2 edges. First, which goes from 0 to 1, and second, which goes from 0 to 3. And there are different costs for the same. And all of this information is stored inside an array list, right? Similarly, what we can do is we can fill details for every other edge as well. Currently, if we come over here, my graph from what I have written over here looks something like this. From 0 to 1, from 0 to 3, from 0 to 3 we have cost of 40, from 0 to 1 we have cost of 10. This is the graph that I have created currently. We can keep on adding different edges to this particular graph, right? I hope you understand what graph is and how we can represent graph, and I hope you understood the difference between adjacency matrix and list and how we prefer a particular one from over the another one, right? So adjacency list gives you space optimization, but adjacency matrix, however, on top of that, gives you lower time complexity to determine whether there is an edge or not, right? So the access to an edge is much more faster than adjacency matrix, however, with the cost of extra space, right? So I will see you in the next video, in which we will be solving another question, which is hash paths, which would be our very first question in graph series, right? See you. Bye bye.